Hello everyone, welcome to the 64th annual meeting of the Australian Mathematical Society for the algebra session. And the first talk of today is Heiko Dietrich from Monash University, who's going to talk about group isomorphism. It seems that he has some comments on that.
All right, thank you. And yeah, thanks to Mikhail and James for organizing this algebra session. It's a pleasure to be the first speaker in this session. So before I start, I should say that everything or most of the things I say today are joint work together with James Wilson, who's a collaborator at Colorado State University. Now, group isomorphism, well, simply speaking, that's a decision problem. You know, you've been given two groups, and all groups will be finite here. And you are asked to decide whether these two groups are isomorphic. Sometimes you also want an isomorphism, but this would be rather an add-on to the actual problem. Now, James and I started working on group isomorphism in, well, I think 4 years ago in 2016. And since then, we're making more and more progress. And this also explains the quite vague title because, you know, I should have chosen the title Group Isomorphism of Most Group Orders, but I used this title last year when I talked about a different angle of this problem. So I didn't want to reuse it. So today I talk about an update of this isomorphism problem. Now, when you talk about group isomorphism, there are naturally, I guess, two flavors. You know, there's a theory point of view, which is the aspect people are interested in when they work in complexity theory or the theory of algorithms. And then there is a practical side of things, which usually is of interest to people who practically work with groups, for example, with computer algebra systems, you know, when you actually want to test whether two groups are isomorphic computationally. Now, these things don't always go hand in hand, as we know. You know, there are some algorithms that have favorable complexity, but they still don't work well in practice, like the AKS primality test, and also vice versa. Now, James and I, we are both coming from the practical side. So we work in computer algebra. So we usually would be interested in being able to compute with groups on a computer. However, what I'm talking about today is more on the theoretical side, because we assume that our groups are input by their multiplication tables. So it's a Cayley table model. So with this in mind, the problem we want to discuss or to look at today is, or can be phrased as follows. So the input to group isomorphism is two n times n tables, whose entries are between 1 and n, encoded as binary strings. And we want to decide whether these tables describe isomorphic groups. Now, when you describe it like that, it's sort of obvious that this description is not too relevant in practice, right? I mean, if you want to compute with groups on a computer, usually these groups are way too large for an enumeration of all elements. And here we hand over the whole multiplication table, right? So from a practical point of view, this is maybe not too interesting. However, group isomorphism for the Cayley table model is interesting for the following reasons. First of all, from the complexity theory, it is known that this version of group isomorphism lies in the class NP. So if someone gives you a witness for an isomorphism, you can test in polynomial time whether this is actually an isomorphism. You just evaluate it on all possible products. But it's not known whether it is in the class P, that is whether you can find an isomorphism or decide isomorphism in polynomial time. One reason why it's quite famous, I'd say, is because it reduces to the graph isomorphism problem, which has had a lot of attention in the past. And the reduction is quite easy. If you have a finite group having n elements, a1 up to an, then you basically set up a directed graph that has vertices a1 up to an and additional vertices aij. And whenever you have a product in your group, ai times aj equals ak, you add the directed edges you see here. And then it follows that your two groups are isomorphic if and only if these directed graphs are isomorphic. Now, graph isomorphism had a breakthrough result recently presented by Laszlo Babai, who proved that graph isomorphism can be solved in quasi-polynomial time. So this essentially means polynomial time, but you have some logarithms flying around as well. So there had been some breakthrough. And on the other hand, as we will see on the next slide, the general complexity of group isomorphism is also quasi-polynomial. And this has been resilient for quite a few decades. So it sort of seems to indicate that group isomorphism is an obstacle for improving graph isomorphism even further. So this is why group isomorphism in the Cayley theory model is still quite interesting. So let me say a few words about what is known, and obviously for time reasons this is highly incomplete. Just want to highlight a couple of things which I think are interested and related. So in 1978, Miller has published an algorithm to solve group isomorphism for the Cayley table model in quasi-polynomial time. He gives credit to Charjan for that. And the remarkable thing here is to observe that it's really the brute force algorithm. So you realize that groups of order n can be generated by log n elements. So what you do is you first find a generating set that has log n elements. And then you basically test, all maps that take this generating set to the second group and check whether one of these maps gives you an isomorphism. So it's really simple and brute force, and it gives you this quasi-polynomial time. Now, this is for general groups, and as I said, it is quite resilient because in 4 decades, the only improvement that had been made is to basically make a better coefficient here in the exponent. Right? So this seems to indicate that it is in general difficult to improve the general time complexity for arbitrary groups, which is also a reason why why work has fragmented into different subclasses of the problem. And I want to highlight just a few of those in this small paragraph. First, I want to point out work of Vikas and Kavita. They have considered abelian groups, and they have shown, so abelian groups and abelian P groups, they have shown that you can solve group isomorphism in time O of n. And the way they've done it is actually quite interesting because they basically show that you can determine the order distribution of your group elements. For abelian groups, the isomorphism type is uniquely determined by the number of elements of a given order. So if you know all the group element orders, you know the isomorphism type, and this is what they have done. Now this is abelian groups. Then there's the work of Babai, Kodenotti, and Tsao. They have shown that if you have a group that has no non-trivial abelian subgroups, normal subgroups, then you can also solve group isomorphism efficiently in polynomial time. Right? So these two results together are quite interesting because they show that abelian groups are fine, and having no non-trivial abelian normal subgroup is fine. So the hard cases really seem to be groups that have abelian normal subgroups. And then there is lots of other work by various people. I'm not going into detail here, but they consider also certain subclasses of groups. Now, there might be a point to wonder, how can Vikas and Kavita solve group isomorphism in time O of n if you work in the Cayley table model, right? There are a couple of problems. First of all, what's the input? The input are 2 Cayley tables. So reading the whole input alone takes n square log n, right? And also, if you work on a Turing machine and you want to multiply 2 elements, well, in the worst case, you have to scan the whole table again to figure out the product. So multiplication also has an upper bound of n square log n. So how the heck can you do something in O of n, which is sort of curious. Now, the thing to realize is that some papers or some authors, they work in different computational models or they make different assumptions. First of all, some algorithms work in the so-called promise hierarchy, where you assume that the input you hand over to your algorithm is actually correct. In this case, it means your tables are groups, right? And realizing that groups are generated by log n elements, you don't have to read the whole input table if you want to get the group. A second thing to realize is that, as I said, there are different computational models. So Kavita, for example, she works in a random access machine where she assumes that the tables are sort of pre-stored in registers, and you can actually perform the group multiplication in unit time. Yeah? So when you read about group isomorphism in this area, it's always kind of tricky to compare because they might use different models and different assumptions on the time. So this is important to keep in mind. All right, so let me say, apologies, a few words about the main results. So drum roll, please. We have seen abelian groups are fine, right? We have seen the groups that don't have non-trivial abelian normal subgroups are sort of fine. What we prove is basically the group isomorphism is easy for almost all group orders. And what's meant by that? Well, here's the theorem. We have shown that there is a dense set of group orders, and dense in the set of in the sense of natural density or asymptotic density. There's a dense set of group orders such that group isomorphism for 2 groups of orders in this set can be solved in time n square and some factors of logs. So usually we ignore these log factors, right? So this is a pretty strong statement because it basically means that almost all group orders you can deal with quite efficiently. However, I should make a comment here, which is appropriate. I should really highlight that theorem 1 only talks about orders and not almost all groups. Isomorphism types of groups are not evenly distributed around all orders. For example, for every prime order, there is only one group. Right? So this is really just a question about orders. What can I say about this DEM set? We'll define it later, but for now, let me just say that it contains all square free integers, which already have density about 60%. And the asymptotic is also not too bad. I mean, I've listed here a couple of first fractions, so the convergence isn't too bad. And maybe most importantly, and what makes our result true is that this set excludes certain order types, namely orders that have large powers of a prime as divisors, and large really relative to the group order, right? So to some extent, theorem 1 is sort of a formal support of the conjecture that P groups are still, the main bottleneck of group isomorphism, really. On the other hand, for P groups, there exists also work, for example, by Lee, Sau, and Wilson, who have shown that, for large classes of P groups, you can actually deal with group isomorphism quite efficiently. So altogether, our result seems to indicate that maybe the average time of group isomorphism might be polynomial time. So I still think it's a pretty neat result. And as I said, it supports this conjecture that P groups are the main problem, but also that overall it might be polynomial time in average. Along the way, we've also produced a second theorem, which is related here. And this goes back to what I said earlier, that some work is done in the promise hierarchy, which we don't have to do here. So in the promise hierarchy, it's I think like that, you have strings for your input, and these strings are either yes instances of your decision problem, for example, 2 strings that are groups that are isomorphic. They can be no instances, which are 2 strings giving you groups that are non-isomorphic, or they could be disallowed strings, for example, 2 strings that don't define groups. Now, the bad thing is that on disallowed strings, your algorithm can do whatever it wants. And in general, it could be that there are strings, disallowed strings, that look like valid strings. So they trick the Turing machine into sort of thinking it is a group or whatsoever, and it produces an output, and then you can't really tell, whether this is actually a correct output or not. Now, for the Cayley table, it's actually not so critical, but this is critical when you talk about, for example, black box algorithms, because often you really can't verify your input in polynomial time. Anyway, so we don't have to work in the promise hierarchy because we proved the following. You can decide whether your input string describes the Cayley table of a group also in time n square times some logarithms. Now, comment on that. There are, of course, existing results of this flavor. All the results we found were sort of cubic in the input size until we were pointed to this work of Raja Gopalan and Schoolman. So an MIT student pointed us to this work after we posted our paper on the archive. This paper claims a complexity of n square log n. But when you look in the paper, they actually use a binary product which is computed in unit time, which is again not something we do. Anyway, so why is this important for us? Well, it really helps us to cast our main theorem in nearly linear time in the deterministic polynomial time hierarchy. So it properly accepts or rejects all strings. So if we would have used n cubed here, then we wouldn't be able to claim it's nearly linear time. All right, so let me say a few words on the proof. The main idea really is to separate 2 difficult problems. So when you talk about group isomorphism, there I think can be really only 2 things that can blow up the complexity. One thing is that the group structure is just too difficult, it's just too intricate, right? The other thing is that the number theory is too hard. For example, you could have large primes, for example, and you have discrete logs showing up. So we thought, well, maybe we can somehow separate these 2 problems. More precisely, we wanted to look at conditions on the group order that allow us to prove that every group of this order splits as a direct, semi-direct product, where the hard or complicated group theory is covered basically by H, and the bad or big number theory, so to speak, is covered by D. So we separate these two problems. And how can we deal with these problems? Well, we want to arrange that the hard group theory has a favorable number theory in the sense that the group order is tiny compared to the input group. So even though H might be a complicated group, the size is tiny, so we can actually use brute force methods to deal with it. And in terms of the bad number theory, well, we want to arrange that the group structure of B is easy. So it turns out that we can arrange that B is a cyclic group. And for cyclic groups, the isomorphism type is determined by the order. So even though the number theory might be bad in terms of discrete logs, etc., the isomorphism type is easily determined. So this was the main idea. And we do this by looking at some number theory properties of our dense set. So here's a question. Which of these numbers is the 1000th prime? Any guesses or ideas? Unfortunately, my chat is down. I can't see it. Where's my chat? Anyone wants to make a guess? C, yeah, good guess. I really didn't know what people would guess. So the thing is, it's actually A. It's actually A. And this is sort of surprising because it tells us, among the first 8,000 numbers, every 8th number is a prime. Right? And because primes are so abundant, it sort of gives you the idea that most integers really factor in lots of distinct and big primes. Yeah? And this has been formalized by a result of Erdős and Palffy, who have proved the following. They've shown that almost every integer n satisfies the following. If you have a large prime a large prime divisor, and large meaning greater than log n, the number theory large. If this prime divides n, then p squared doesn't divide n. Yeah? So this really says that for almost every integer, large primes only divide the number once, not twice. And this is the basis really of our main theorem regarding the orders we consider. So what you see here in red is really just a formal way of writing down Erdős and Palffy. We say that the following set of integers is dense, those integers that factors a times b, where a contains all small prime divisors of n, and b contains all large prime divisors of n. So this is just Erdős and Palffy. We want two further properties. We want that the prime powers that show up in A, that these guys are also small. So we want that these are bounded by log n. And we want that the large prime divisors, which we have in our factor b here, they are what's called isolated. So I'm not really going into detail here. It's just some divisibility conditions. So let me skip this for time reasons. But what we proved is that even with these additional red properties, the set is still dense. So this is our set of orders we look at. Right? So we have all the large primes, they occur only square free, and all the other primes, their powers, they are also bounded by log n. If you have a group of this order type, then the group structure is highly restricted. And this is what we prove. So if you have a group of this order, then we have indeed the decomposition I was talking about earlier. We have that this splits as a semi-direct product. Here it turns out that B is some normal Hall subgroup and H is some complement. This Hall subgroup here, again, I'm skipping some details. It's with respect to some large primes, the primes that are greater than log n, plus some additional properties. And the most crucial bit really is what I've highlighted now in red. This normal subgroup B is cyclic, so a very easy group structure. And the complement is tiny. Yeah? So the group size is very small compared to the group size of the input group. So proving this result here really took most of the time, and I'm skipping a hell lot of the details here. But if you assume this as given, then the main argument for our algorithm really is as follows. You realize that two of these groups are isomorphic, implies that the H parts are isomorphic and the B parts are isomorphic. Now, the H parts, as I said, they are tiny. We can even just use the brute force algorithm to check that they are isomorphic. And if you know that these are isomorphic, this tells you that the B parts have the same order, but the B parts are cyclic. So having the same order really means they are also isomorphic. And then you can identify the H and B parts, and eventually you only have to compare, split extensions where you have different group actions from your small group into the cyclic group. And because H is small, you can also do this brute force. So this is really the main argument once you have this theorem established, And when we shared our preprint with some experts in the field, we received some nice feedback. For example, Joshua Grocho, he said, not only is group isomorphism solvable for most orders, but it's also solvable by a pretty simple algorithm, which is true, because basically it's essentially still brute force. We just had to do a lot of work to get there. All right, so that's basically the main idea of our proof. I want to conclude quickly by saying that this whole group isomorphism project, which I'm working on with James for a couple of years now, also has some practical outcomes. Now, last year, I talked about theorem 1 in the black box context for abelian and certain metacyclic groups. And this made me start working on some metacyclic group with an honor student. So we looked at what's called C groups, sometimes also called Z groups. These are groups who only have cyclic pseudo subgroups. Due to Hölder, Burnside, Sassenhaus, it is known that these groups are metacyclic, right? So we started looking at that and wanted a practical algorithm to solve isomorphism problem for them. And this is what we came up with. So maybe I should say, first of all, that all this is motivated by work of Slattery on square-free groups. So square-free groups are metacyclic, and obviously they have cyclic pseudo subgroups. So basically we have generalized Slattery's work to groups who have cyclic pseudo subgroups. So what we can do is well, we can construct for any given order, we can construct a list of all C groups up to isomorphism. And importantly, we can also construct like the ith group in that list without constructing the whole list. And similarly, if you give me some other C group of order n, we can immediately determine, or not immediately, we can directly determine which position in that list this group is isomorphic to without constructing the whole list. So this gives us a group ID, so to speak, and a dynamic database. And our next speaker, Eileen, will probably talk a little bit more about that. She's just speaking about after my talk. Just to finish off, let me just illustrate how well this works in GAP. So for square-free orders, our implementation is generally faster than GAP code, but for non-square-free orders, it's also quite good. So here you have a large non-square-free order. There are 6,006 isomorphism types of C groups of that order, and it takes us 4.6 seconds to construct them all. And then we went on and we took isomorphic copies of these groups, and we wanted to identify them all. And this took like 47 seconds for identifying all these 6,000 groups. So this is working quite well, actually. All right, so I only present this here to show you that even though most of the other work I did with James is more on the theoretical side, there are some practical spin-offs which are actually useful also on the practical side. Last slide, just a conclusion, some references and a brief outlook. So James and I continue to work on this. We want to generalize theorem 1 to other input models, in particular black box models. And there it will be even more important to consider, moving away from promise problems. So this is one thing we try to focus on right now. So that's all I want to say. And I guess I wish everyone a good break. Thanks.
Thank you, Heiko. Are there any questions? Well, if not, let's thank Heiko one more time.
Silent. Thank you.